Okay, so you've gone through the basic, and we've learned a lot about supercells and weather safety. So this is going to be kind of taking it to the next level. Some of it may be over your head, some of it may not. I'll try to helpfully explain in very simple terms what we're going to be talking about. We're going to concentrate a little bit more on supercells. Supercells are such a major contributor to some of the most significant of severe weather. As an example, the tornadoes that we had on October 30th by our office was caused by a supercell. That big tornado that they had on December 26th in Dallas, the EF4 tornado, was a supercell thunderstorm tornado. If you remember, March 25th is a very famous date in Austin's history for weather. The 3 largest hailstorms in Austin's history have all happened on March 25th, on 3 separate different years. Those were all typically all supercell storms that produced all that big-time baseball-sized hail. So overall, they just contribute a whole lot to the most significant of our severe weather. So we'll kind of concentrate some of that today. So remember, so we're going to talk about the review of the supercell. We'll talk about storm development again a little bit more. And then toward the very end, we're going to talk not only about spotter placement. So basically what that means is that we're going to show you what the radar looks like and then where you would be and what you would see, especially on a big, large supercell. So you kind of have an idea of what you may see in different locations. And then finally, we're actually going to go over a few of the different radar products. So many of you probably have a weather app or something on your phone that can watch radar. And many times, some of those radar apps have got multiple product listings, composite reflectivity, base velocity, and all these other things. I'm going to try to explain a few of those in simple terms so you can kind of understand what those are. Okay, so again, for the supercells, nearly all of them are severe. Going back and looking at research with actual supercells, only about 20% of supercells actually produce tornadoes. Okay? But the majority of them, upwards of 80 and 90% of them, produce severe weather, like the golf ball size hail, like the big microburst winds where it's wind damage and everything else. So they typically are always severe. It just depends on whether or not they're actually going to produce an actual tornado or not. Many times inside that supercell itself, the rotating updraft, which we call a mesocyclone, can be upwards of 5 to 10 miles in diameter. And this rotation actually helps increase the hail size and the amount of wind and the wind mile per hour that actually comes all the way down to the ground. And like I said, about only 10 to 20% or 10 to 15% actually produce tornadoes itself. So they're very important thunderstorms. Many of ours will come primarily from the west. They may develop more out into the big country of Texas, where you're talking about San Angelo, Abilene, and actually come through places like Llano, Burnett County, then eventually come through Austin. And then right around here, the I-35 corridor, sometimes those supercells start to transition into other forms of a thunderstorm. So it's not as common to have supercells here in Bastrop County as it is maybe out to the west in hill country, but it's still very, very possible to get a supercell that comes all the way into Bastrop County. So again, the ingredients for the thunderstorm, we talked about this, the humidity, which is the moisture, the instability, the lift, and then of course that jet stream and the wind shear. So where do we get most of our moisture from? Most of our moisture will come from the Gulf of Mexico. If we have several days worth of southerly winds or southeasterly winds, in about 2 or 3 days, we will typically have enough moisture outside, meaning it'll be humid enough to actually get thunderstorms to form. This time of year, we get a lot of cold fronts, which means that we get a lot of north wind. North wind and west wind tends to be dry. So right after a cold front, you don't really get a lot of rain because the moisture just isn't there. But in particularly, our source region is the Gulf of Mexico. You may have heard also, especially in parts of the winter time or even in the fall, we get a lot of moisture from the Pacific Ocean. And that is very often. Some of our big rainfall events that we've had in the fall is not only because we have moisture from the Gulf, but we also get moisture from the Pacific Ocean with like a landfalling hurricane on the Pacific coast. If you remember, that actually happened the week before the October 30th flooding. We had a massive rain event of 8 to 10 inches of rain, but it happened all weekend, and it was beautiful rain. It was soaking in rain, quarter inch an hour, and it didn't produce any flash flooding. We had 10 inches of rain, no flash flooding. But believe it or not, it was that event that really caused the October 30th event. Because the ground was already saturated, when we got the big rains on October 30th, it led to all pure runoff. So sometimes it just happens that way. To measure the moisture, we actually track more the dew point. You've probably seen that on TV. Well, what's the dew point? Well, it's actually the temperature to where dew forms or fog forms on the ground. And so typically, when we get dew points upwards of 60 degrees, that's when it becomes uncomfortable outside. But that also begins to become almost the trigger where we'll actually get maybe some thunderstorms. We can have thunderstorms in the middle of the winter. We've actually had sleet storms where it's been thundering and lightning and it's 40 degrees outside. So as long as the atmosphere is unstable, you can still get actual thunderstorms to form. So of course the instability is kind of, I have a picture there of the warm air, of the hot air balloon. Think of it this way. As long as that air is warmer than the surrounding air, it will rise. That's how a hot air balloon works. As long as they can gas up the inner part of the balloon where that air is warmer than the surrounding air, it will continue to float up. And so that's what kind of atmosphere we actually need, is to have an unstable atmosphere. This is kind of how our typical atmosphere looks, where we have warm and moist air at the ground level, we have cool, and then even colder air aloft. So, you know, where the airplanes fly up here, you know, we're talking it's minus 40, minus 50 degrees. So this is typically an unstable atmosphere. Warm air rises, cold air sinks. That's why you reverse the fans in the wintertime to try to get that warm air back down to the ground. Okay? And so as long as that air parcel is able to continually go up in the atmosphere, and even think of it this way too, if that warm air bubble starts here, this bubble air will still be very warm compared to the air surrounding it. That's why it'll continue to rise up. So again, that's called an unstable atmosphere. Sometimes the atmosphere is so warm in this mid layer here that it creates what they call a cap. And the cap is actually very important in severe weather, because if thunderstorms start to form too early in the morning, like it's very unstable and we get thunderstorms, they can never build up enough energy to really be that severe. We'll get rain and we'll get thunderstorms, but you literally need, and I always kind of like to describe the Tupperware in the microwave. Okay? If you don't pop open that lid and you have it sealed up and you put that thing in the microwave, what happens when it heats up too much? Right? It kind of explodes up and you have a mess in the microwave. Think of that with the thunderstorms. You need just as much cap in here to where eventually, if it does get warm enough in the day or something comes in, all this energy will be built up and then finally it'll just explode up. And that's what will trigger that huge development and quick development of an actual severe thunderstorm. So you still require lift like a cold front, but then some days for us, especially this far south in Texas, we will have too strong of a cap, which means nothing goes up. We may even have a tornado watch out, a severe thunderstorm watch out, and yet a storm will never form because we are this close. If it just would have heated up 2 more degrees, it would have broken the cap. But a lot of times, the cap is just too darn strong.
How do you guys, meteorologists, determine what the cap is?
The weather balloons. The weather balloon launches that we do across the world will give us a fairly good idea of how strong that cap is that day. But then also, the weather models then will also forecast that cap. So yeah, the weather balloons that we launch every day is giving us already that exact of what the temperatures are at all the different levels.
Do they do that in ground pools?
We do not. The closest launch sites we have are Del Rio, Corpus Christi, and Fort Worth. There's a little bit of a hole right here in south central Texas. So we kind of have to extrapolate a little bit and use the weather models to fill in the blanks. Yes, yes. Yep, exactly. So that's what it is. It's potential energy. Which water balloon has the best chance to burst when it hits the ground? Well, it's obviously this one. It's coming from a further distance. So on a more scientifically, which balloon has the higher potential energy? It's this balloon here. Okay? And so speaking of weather balloons, good segue, this is an image that we actually get from one of our weather balloon launches. Okay? We call this a Skew-T. And so this is a plot that we learn in meteorology. And so I'll explain this here in a little bit, but basically from these diagrams, we are able to view and to calculate the potential energy that a thunderstorm may have. And we call it CAPE, convective available potential energy. The CAPE is this colored in area right there. We used to do this by hand when I came into meteorology. Now we're lucky that the computers do all this for us, that we don't have to physically calculate all these different things. But the more CAPE you have, the stronger and faster developing storm. Okay? During the winter here, it's hard to get a lot of CAPE, so we have very typically minor thunderstorms. But as we get hotter during the year and we get more instability, that's where it goes up. So yeah, so the weather balloons measure the CAPE in the atmosphere using what we call a Skew-T diagram. So, excuse me. So this is a plot, raw plot of weather balloon data. The red line here is actually, I'm sorry, I'll go this way first. All these lines going across are pressures, lines of equal pressure. So typically 500 millibars is somewhere roughly around like 18,000 feet up in the atmosphere. Also on this, we have lines of temperature. Okay, so this right now I've highlighted the 0 degree line, so the freezing line in the atmosphere. Right there, this curved line is called a dry, help me out, a dry what? Adiabat, thank you. Dry adiabat, which means that if the air is rising and it is not saturated yet, the air parcel will technically travel along this boundary. This curved line is called a moist adiabat. So as soon as the cloud forms, it will continue to rise, but now on this line, this plot here is the raw plot from the weather balloon of the air temperature. So as you go up in the atmosphere, it tends to get colder and colder and colder. So as an example, right here where the 0 degree line crosses there, right at this level is where the atmosphere goes below freezing. Think of it that way. So everywhere on this part of the diagram, it's colder. The atmosphere is actually colder than the weather balloon. On this side, it's actually warmer than the weather balloon. Okay? And that's going to become important. This green line here is actually the dew point temperature of the air as the weather balloon goes up. So the weather balloon actually measures a dew point temperature, it measures the air temperature, it measures pressure. Okay? And so it figures out those three things, and it sends back that data continually. And then we also track the weather balloon so we can pick up the wind speed. So just like using math where if the balloon is over Bastrop at time 1, and then 10 minutes later it's way over there, it figures out how fast the wind must be blowing to blow the balloon that direction. And the balloons are actually now GPS. So we get very, very accurate readings when it comes to the wind measurements with that. So let's create an air parcel. So there's a big parcel of air here in Bastrop, and this is what the sounding showed this day. And we're going to have a means of lifting this. Maybe a cold front is coming, okay? And it comes in, and it literally is going to push up this parcel of air. And so we're going to see what it actually does. It's first going to follow a dry adiabat for a little bit, and then it becomes saturated, and then it's going to go all the way up there. Okay? And what this is going to do, that's going to be the trace of our parcel of air. That's where it went. Okay? And it actually went to the right of our actual temperature plot. And that is going to be the potential energy. So as you can imagine, as the parcel went up right here, it was warmer than what the air around it is. So again, it's going to continue to rise because it is warmer. So that's how we actually average out and create our potential energy for the day. Now there's some other things that can happen to then, during the day, increase the amount of potential energy that we can actually get from a thunderstorm. It could actually get warmer during the day. So if it gets warmer at the surface during the day, we could actually get even a larger thing. So think of it this way. If we are forecasting the temperature to be 90 degrees, that gives us a certain amount of CAPE potential energy. But if the high actually gets up to 95, that creates more area in our sounding plot here, which means that the temperature and the storm will have more CAPE. It could be a bigger thunderstorm. It could be a more dangerous thunderstorm. It could have more potential energy. So just heating of the day could increase the amount of CAPE that we have. And then also, if there's a disturbance in the upper atmosphere that comes in, it could actually make the atmosphere colder. That's what an upper level disturbance is, if you didn't know that. It's a pocket of cold air. So if that disturbance comes over us and it gets hotter at the surface and it gets colder aloft, that's actually expanding it in both directions. So in this case here, I'm actually cooling the atmosphere, so I've brought the line this way and that way, and I've carved out even a larger chunk of CAPE. And that very well what happens in the spring when an upper level disturbance comes. It'll start cooling down the atmosphere, and that naturally just creates more CAPE. Yes, sir? If you would be able to track the speed of a cloud, and you can, by satellite, at levels of the atmosphere, you could use a tool where you would have a satellite picture at one time, satellite picture at the next time, and figure out how fast that cloud moved, that yes, you could actually estimate wind speeds. You could do that with any sort of cloud, at the ground or a contrail from an airplane. Okay, but you have to have something there for it to be tracked, for the wind speed to actually be tracked.
Now, assuming the contrail tells you it's moist.
Correct? Correct, yes.
Anything else that would billows out?
Not so much when it comes into severe weather forecasting like that. But very often you have to, in areas where you don't have weather balloons, like in the oceans, You don't have us launching weather balloons everywhere. We actually use some of our newest, most expensive weather satellites to replicate a weather balloon launch solely by using these satellite. And they're becoming very, very accurate. So we can fill in a lot of gaps now over the ocean by getting data by using a satellite. It can replicate a weather balloon launch, which is kind of crazy to think about. That's so much more data now getting fed into the models. That's why the models are becoming more accurate. We're getting more data into the systems. Okay, so let's go on. Let's talk about lift. Lift, the spark plug that sets everything off, can be in several different forms. It could be a cold front. It could be this upper level disturbance and the jet stream coming across creates lift. It could be a surface cyclone like that. So there's various sources of lift in the atmosphere, but most common are the front. So our next good chance of rain, and it's not very good, is going to be on Tuesday. We're going to have an upper level disturbance come across North Texas. We're going to have a cold front at the surface, so we'll have a couple of triggers. Our one issue that we may have of not getting rain is that we may not be unstable enough. There's actually forecasted to be too high of a cap, too much of a warm air layer, to where the lift is going to be there, but it's going to come up there and it's not going to be able to burst through that cap. It may just be held. So we're going to have to watch out. That's why our chance of rain is only like 20 or 30% on Tuesday, even though you have a front, humidity the day before, the south winds. Would you think we're going to have all the ingredients, but that cap may come into play and we just may not have enough lift to break through that cap in the atmosphere. So this is the cold front. This is what it looks like. It's a big steep kind of slope of cold air which forces air up ahead of it. That causes lift. So let's talk about wind shear. We talked briefly about wind shear being one of the new ingredients that we needed to get severe thunderstorms. Let's describe a little bit more what happens. So wind shear is the difference in wind speed with height. So in this example here on the right-hand side is where airplanes are flying 20, 30,000 feet up. The wind arrows are representing the wind direction and wind speed. Okay? So we can have a couple of different types of wind shear. We can have speed shear, meaning that the winds are much stronger way up there as opposed to the ground. And on a good severe weather day for us, we may be blowing at 20 miles an hour at the ground, but up at this level here, the winds may be 100 miles per hour. So the jet stream is up there. So that's a big shear, 20 mile per hour compared to 100 mile per hour. Now another big ingredient, especially in getting supercells and ones that produce tornadoes, is to have directional wind shear, meaning that the wind direction changes with height as well. In this diagram here, we have wind coming out of the, let's say, the south-southeast near the surface, and as you go up in the atmosphere, it turns to a southwest wind, a west-southwest wind, and then a due westerly wind. That turning is called a veering wind, and so that will actually help aid the production of supercells and the rotation within those supercells as well. Okay? There are some days where we just have speed shear. We'll actually get really big squall lines with that. But if you have speed shear and directional shear, that's where supercells really are starting to get forecasted and have a very high probability of occurring. So wind shear is not needed for storms to develop, but the higher values of wind shear typically means a longer life, a longer living storm. So just like we described in the beginning, if there's not a lot of wind outside, the storms go up and come down like this. But as soon as you increase this wind speed aloft, that's where the storms can last hours. And I've worked several instances in my career where there is one particular supercell, and it formed. I was in Charleston at the time, Charleston, South Carolina. It formed in the Gulf of Mexico, came on shore, the Florida Panhandle, crossed the entire state of Georgia, the entire state of South Carolina, and North Carolina, and then went off the Delmarva. One thunderstorm, moving that far, and lasted about 12 hours. So that was in perfect balance. The fuel and exhaust, it was in perfect balance of a thunderstorm. And so that's why they can last so long. So this is what it looks like with weak wind shear, up and down. Again, the rain comes down, collapses, and it rains itself out in an hour. Okay? Up and down, again, right on top of each other. But look at this nice picture here. The winds are so strong here, coming from left to right, that literally that updraft is trying to form and it gets pushed off to the side. All the wind and hail is blown way off to the side. The updraft is still here with the fuel, and you can see because of this distance here, they don't disrupt each other, and so you could have a very long-lived thunderstorm. This one is almost, there is so much wind shear, it looks like it's almost kind of not forming very well, and we kind of talked about that. This is a schematic which is going to show how the this wind shear can actually create the circulation of the actual atmosphere itself. When you have winds aloft that are strong and winds that are not so strong at the surface, it will naturally cause a turning like this in the atmosphere. Think of a water wheel, okay, or think of if I have a paddle wheel and I have strong winds at the top, it's going to spin like this. And so that's actually what happens. There's these horizontal rotors. Let me go back. There's actually some horizontal rolls that develop in the atmosphere like this. And if there happens to be a thunderstorm that develops on top of that roll, it's going to be tilted upward. And those horizontal lines actually turn into a vertical. So watch here, as a thunderstorm forms on top of this, it's going to tilt this horizontal tube into a vertical tube. And thus, a rotating updraft is born. Okay, so again, on a windy day where you have winds at the ground but very windy aloft, you'll naturally just have these rotors in the atmosphere. That's why it's always so bumpy when you're flying in an airplane on a windy day, is because literally those changes of winds will cause all these rotors that are happening like this. But yeah, it's a tilting of this tube. And so the tilting, and so then you have a counterclockwise rotating portion of the storm here, and then actually a clockwise spinning rotation on the other side of the thunderstorm. When you have this, believe it or not, some of these supercells can split. They can split into two. We don't have a picture of one, but they call them splitting supercells, to where literally one big supercell will occur and form, and then minutes later, you'll have two of them. And then the two become four. And the four, it's kind of freaky. It's like biology class when you're looking at cells multiply. And what's interesting about that is that the one that is spinning counterclockwise is the one that we call a right mover, and that's the one that typically lasts. The left mover, because it's actually a clockwise spin, doesn't usually have the best moisture with it and the instability with it, and so it actually winds up kind of dying out a lot of times. So many times the one that survives is called the right mover, and it's called the right mover because it moves to the right of where all the other storms are moving. So literally you could have a thunderstorm that is moving this direction like this, going up on the map, and then all of a sudden the storm does this and takes a right turn and does that. And those sometimes are the most severe ones that we actually have. So here's a thunderstorm. It's starting to form, and this is going to be the supercell forming. Again, the wind shear is so strong it's shoving all that cloud and all the rain and hail. It's going to be falling way over here. This is what it's going to look like when it develops. This is very similar to that actual live video that we showed you of that supercell coming toward in the basic class, where you see the beautiful rotation and everything else. So here's all the rain and hail, all the blow off. So the winds are very strong at this level here, blowing all the cirrus way over here. But this area, there's the flanking line. This is the rain-free base. This is the rotating updraft right here. So there's a lot of stuff going on during these thunderstorms. And so this is an example of one of the violent supercells that we had. This was the Joplin tornado. Notice this is kind of really messy looking on radar. This is not the typical just, oh, I see the hook, kind of a thing. But actually, if you look at it, here is the hook right there. There's other thunderstorms around it, so it's not so easy to see. But when you look at it, right there is the hook. And right there, that white spot right there is called a debris signature. And so what is happening is the tornado was picking up chunks of stuff, putting up in the atmosphere. The radar is hitting it and thinking it's like large hail or really big raindrops, when in fact it's stuff. Lumber, rocks, cars, everything that these big tornadoes actually pick up. So this is the devastation that happened in Joplin, Missouri. And what we do is we look at the velocity data and we match it up with where that is. And if you have the velocity couplet right next to where we think that white is, we're going, uh-oh, because that's a signature of a tornado. And if we're seeing that, well, that means that that tornado is probably on the ground and it's lofting debris up into the atmosphere. We call it a TDS, a tornadic. Yeah, there you go. Oh, see. Another violent supercell. This is going to be Moore, Oklahoma. This is more of the classic sort of supercell with a hook like this. And again, where this ball is going to be toward the very back edge of the thunderstorm to the southwest side, right there is a tornado on the ground approaching and going through Moore, Oklahoma. So again, this is kind of the example of what we had at Moore, Oklahoma. Here is the velocities that we see on there. So again, go ahead.
People may not know those are two different directions on the wind speed.
Correct, correct. Yes, the red and the greens are the cool colors of the green is coming toward the radar, and the red is actually going away from the radar. So that's typically how we will actually view the velocity data on the radar itself, like that. So where the reds and the greens are right next to each other, right there, matching it up with what we're seeing in this picture here is where we can determine typically if we have a very high likelihood of having a tornado. You know, so if we're not already getting spotter reports from something like this, we would be issuing tornado warnings solely based on radar. Again, no guarantee that there's something happening at the ground. That's where you guys come in, reporting it, or we're seeing it on TV, etc. Okay. This is a picture from the El Reno tornadoes that occurred. The El Reno tornadoes were very famous because this is actually where one of the storm chasers died a couple years ago. Okay. Watch the big circulation. They estimated that the width of this tornado was well over 2 miles. Okay, it's the widest tornado they've technically ever measured. These images that you're seeing here are from one of the newest radars that I don't think we're going to see it by the end of my career. They're called phased array radars. It is not rotating. It is just constantly shining out. So these are images that are occurring about every 10 or 15 seconds. Right now we get an image about every 5 minutes. So you can imagine all more that you see in a thunderstorm if you get 10-second images instead of one every 2 or 3 minutes. They are moving the entire radar on a pedestal like this. So typically a phased array radar can shine in every direction, but they're so expensive we have one side of it. So we got, I think the military gave the Weather Service radar for testing, and they gave us one side. They didn't give us all, they didn't give the rest of them, they gave us just one side. So we have to physically move the entire thing to follow the thunderstorm. So it's research mode right now. It's research for doing, but we're seeing things within these thunderstorms using this type of radar that are extraordinary. And I'm hoping that it will change the science, especially with tornadoes and severe thunderstorms, if and when we kind of get this type of radar into the system. Yes, yes. And again, because you're getting pictures in the realm of seconds instead of minutes, it changes everything, because the tornadoes that form and dissipate within 2 minutes, now you at least have 10 pictures of that, whereas right now we have no pictures of it. Okay? So this was an example of this tornado. This was the velocity. This was the large supercell rotation. This was the whole updraft. These red dots represent chasers. Okay? You can understand why somebody died. When you have a tornado that is literally miles wide, and look, it came actually and it moved this direction, moved southwest. The whole storm was moving primarily this direction along I-40, and then all of a sudden the tornado shifted and actually moved to the right, caught all these people. Okay, and so that's where the fatality actually occurred. So this is why chasing is so dangerous, especially in areas where it's crowded like this. In Oklahoma, it's crowded. When there is a moderate risk or high risk of tornadoes on a particular day, I mean, literally chasers will drive 1,000 miles to get to that location because that's where they want to be. And you get on these back county roads where there is 2 lanes, dirt roads a lot of times, and you have 3 miles worth of cars. Try to reverse everybody in 2 minutes and get them out of the way. They can't do it. So there's actually some places in Oklahoma where they are, I'll call it banning chasing, where you will get pulled over because the sheriff and the law do not want you in that county. They don't, because you're just clogging up the highways. You're causing danger is what you're doing. But yeah, that's the danger. These tornadoes that you don't know actually what path they're taking. So yeah, so maximum path was actually 2.6 miles. Path length was 16 miles. So there's a really good view of a supercell, idealized view, class of supercell from the right flank, meaning, again, this is the rotation updraft right here, the rotating updraft. Again, no rain coming from it because it's all going up, but then all the wind and rain and hail is being blown way downwind like that. So there's the updraft, there's the downdraft. That's the action zone right there. That's typically what is causing a lot of the rotation to actually form and cause an actual tornado itself. So let's kind of talk about the life cycle of a tornado. There are going to be times, and you've probably maybe even seen pictures or videos of this, where there's actually 2 tornadoes on the ground at the same time, especially within a supercell. And literally what is happening, the supercell is becoming cyclic. It's going through a cycle. It's regenerating its tornado. And so you'll actually have one tornado in the dying phase, while another tornado is actually in the formative stage. And when they snap that picture, they see two tornadoes, but one is dying off and one is forming, taking its place like that. Let's talk about where this is actually going to occur. Okay, here's the action zone. Here's the updraft here. All this warm fuel is coming in. This rear flank, it's called a rear flank downdraft. This is, while most of the downdraft that we typically have talked about already is in the forward part of the storm will be moving this direction. This is where typically the shelf cloud is, the downdraft, the hail, the rain. Well, there's a different downdraft we've not talked about yet. It's called the rear flank downdraft. And literally what is happening is that the winds aloft are so strong, they're coming and they're hitting the updraft. It can't penetrate it, so it's being forced down to the ground. So imagine the upper level winds on the jet stream coming, and this big 50,000-foot thunderstorm is in its way. Some of the wind goes around it, some goes up and over it, some goes down it. And that downward wind comes all the way on the ground, and it's called the rear flank downdraft. This is what you would see in front. There's a shelf cloud right there. Okay? Oh, I'm sorry, we're talking about this area down here. So there's the wall cloud, rear flank downdraft, okay, would be right back down here. So this is the area of interest where you'd be looking for the funnel, the wall cloud, the rotation, anything that would be then becoming a tornado itself. And there is kind of a nice wall cloud forming right there. So now the tornadic stage, the tornado is forming. Here's that hook, that famous hook that we talk about on radar. It's getting kind of wrapped up. Again, warm fuel is coming in. So if you're standing right here watching the storm approach you, which is not a good spot, okay, the wind would be at your back coming into this thunderstorm. So it would be flowing into the actual updraft itself. And then if you're over here, you may be getting already hit by westerly or northwesterly winds watching the thunderstorm actually develop from that area there. And this is what it would look like. Good tornado on the ground. Here, you can almost see some blue sky in here. You can imagine this. This is really strong wind that is pushing in through there. So this is the rear flank downdraft that is coming in and that is kind of wrapping around. All right, like that. It is very often sometimes that you will find tornado videos with the sun shining. And that's because that tornado is happening on the back edge of the storm. Most of the storm and rain is all up here. This is maybe even blue sky right back here behind this thunderstorm. So if the sun is setting late in the day, you will have a sun-illuminated tornado. It makes it very picturesque and everything. It looks very beautiful. That's because it is happening on the back side of the thunderstorm like that. And of course, this whole tornado moves with the main storm. So a lot of times, like, I don't know if you saw, Virginia just got hit by some tornadoes. North Carolina did the last couple days. They had some killer tornadoes there. Some of those storms were moving at 75 miles per hour. If the storm is moving at 75 miles an hour, the tornado is moving at 75 miles an hour. And that's why that becomes so dangerous. You cannot get out of the way in time of something moving that fast. Okay? So this tornado is now wrapping up while actually a new updraft and a new tornado may be forming right here. So this is how sometimes you could actually have two tornadoes forming at the exact same time. One is dying out. This cold air is wrapping around it from the rear flank downdraft, while the new one is going to be occurring right there. And look at that picture there. This is the dying storm. Sun is actually starting to illuminate this. That's why it's so white. And then the new tornado, which is even getting stronger here, would be this one right there. So that's the new one. And then this is the old one, right like that. So the occluded tornado typically moves to the left, while the new updraft in the storm will continue to move this way. I worked a storm a couple years ago down southwest of San Antonio where we had damage. The supercell moved to the northeast, but yet every tornado track I had moved to the northwest. And so I had 3 tornadoes. It was one supercell. And so what was happening is that the tornado was weakening and getting, imagine the spinning, kind of spinning off that way, while a new one formed up ahead of it, and then spun and dissipated, and then spun and dissipated. So I had 3 separate tornado tracks moving to the northwest, while the whole storm moved to the northeast. So kind of interesting how that happens. So sometimes you just don't know which direction that tornado is actually going to move. I would have thought I would have found northeast track tornadoes, but in fact everything was about 90 degrees off to the left. So here's kind of a visual of that rear flank downdraft. Again, winds are coming from this direction here and going up and around, but then some is forced down. And so they actually are believing now that this rear flank downdraft is key to actually getting a tornado to form. One part of science and physics is that if you have a very wide spin, If you shrink it, make it skinnier, it has to speed up in rotation. The ice skater is the prime example of that. When the ice skater spins, first, they usually have their arms out and they spin kind of slow, going around, and then what happens when they tuck their arms in? Very fast. They spin up like a top. Okay. So in a mechanism of an updraft up here, which is 5 miles wide, if there's a mechanism which makes it skinnier, that could actually speed up the rotation. How do you make a rotation skinny? Think about a big piece of twine that you're spinning like this. What happens when I taut it like this? It goes whoop, like that. So you can also stretch. If you stretch the column, that will make it spin faster as well. So what happens, literally air will come down and elongate and stretch out this column of air, and that will tighten the rotation too. So they think that that's why this air coming down the thunderstorm is so key to actually getting a tornado developed, because it actually stretches the updraft and it makes it longer, and because it makes it longer, it gets it skinny and it gets it a tighter rotation coming down. So rear flank downdraft. So here's something on radar. Here is the hook that you see here. This is the inflow. There's the forward flank downdraft. Okay, this is more downdraft coming in. This is the rear flank downdraft coming around. And again, this is what you're going to be looking at a rear flank downdraft. All this rain and hail coming, possibly even wrapping around, coming on the back side like this. So let's talk about some of the spotter positions of where, if you do see something this large of a thunderstorm, where you should and should not be. I talked about blue sky and the sun. Look at this. All the rain and hail is way up here, upstream of the thunderstorm, and look at this tornado, right on the back edge like this on the thunderstorm. That is very, very common, typically, especially with these big supercells. So a perfect spotting position is obviously not in the middle of the hail core and the rain, but 1 to 3 miles away from the hazard. But you don't have to move to stay safe. That's where the typical safest place is. We don't want people to be mobile, meaning I don't want people to continue to chase it, especially around here with the low water crossings. So do your best to stay put and be a weather spotter and not try to be mobile and go out there. So let's talk about spotter placement again. So we'll assume that the thunderstorm is moving this direction. Okay? So we're going to call this the right flank. That's going to be called the forward flank because it's in forward of this is the left flank and this is the rear flank. Most tornadoes with these supercells do form on the rear flank, okay, right back down here. Now, most storms do move this direction when it comes to severe thunderstorms, especially from a west to east direction, because that's where the upper level winds are. Who knows the history of the Gerald tornado? Did the Gerald tornado move to the northeast?
I believe
It moved down to the southwest. It moved down I-35. That supercell, believe it or not, formed on a day where there was no jet stream. There was no significant wind shear. But yet you had this massive supercell that developed that caused an EF5 tornado, and there was no wind shear. The reason for that is because it was so unstable, massive amount of potential energy that day, that when you have days like that where it's so explosive of a thunderstorm, that wind shear ingredient is no longer important. It can create its own wind environment inside that storm. And so there are a couple of historic tornadoes, the Gerald tornado and the Plainfield, Illinois tornado that formed when the Capes, and I'll give you the Cape numbers for a good severe weather day is upwards of, let's say, 2,000 or 3,000 joules per kilogram. The Gerald day and the Plainfield, Illinois days were upwards of 6,000, 7,000, 8,000 Cape. And they'll actually know that when they launch the weather balloons, there may not be any wind shear aloft, and they'll still issue tornado watches because they know of the massive amount of Cape that's available. You could get one of those big, massive, deadly tornadoes. So, you know, there's always a possibility of something kind of happening in the atmosphere. And so that's a key. So it can happen even on when you don't have the wind shear. You can still have one of those really big, gigantic tornadoes. Yes, you can, right. The Storm Prediction website, the Storm Prediction Center website, they actually have those Skew-T diagrams for every launch site in the United States, and it has those numbers and everything like that. So yeah. However much you want to weather geek out, there's a weather site for you. I'll tell you that right now, right? Is there an app that has the Cape on there? I don't know if, I'd be surprised if there isn't. I'm sure there's something out there that will list something. Yeah. So this is the flanking line. So this is the updraft clouds, rear flank downdraft. Again, the supercell motion is going typically off to the northeast there. That's going to be the action area. That's where we're going to be paying attention to. Okay? So, key points, the left flank out here. Okay? Generally not a good place to spot anything because you're blocked. Again, you want to be watching a possible tornado developing here. And if you're here, you have to look through all that rain, and you're not going to be able to hardly see anything at all. Okay? Like this. Yes, you can see the big tower going up, and it's a big thunderstorm, but you can't see through all of this stuff to see the action zone, which again, you want to look like right there. Okay? That's all the anvil blowing off, but again, you can't see the low-level features. Back here, okay, this is a good position, okay, because then you're pretty close to the action zone. Hopefully the storm is moving that direction. Know, first of all, which direction it's moving before you decide that you think you're in a good position. Gerald tornado, that's a really bad position, okay, because it's coming right for you. But in this case, we're assuming that the tornado is going that way. Okay? You can see the action area. However, the action area clouds may be tough to see the dark and heavy rain clouds behind it. So, so this is pretty good. Okay? Here's a disorganized wall cloud here. There's a big lightning bolt. Okay? The tall grass here shows all the inflow getting sucked into the actual updraft right there. So that's pretty good. The storm is moving away from you. Okay? Now, you're even closer right here. Now, this is getting a little too close for comfort, probably. But here's a rear flank downdraft shelf cloud. We talked about shelf clouds being in front of the storm. Well, with all that wind coming down and hitting the ground and stuff, it can actually cause another shelf cloud on the rear flank back here with that. Okay? So let's look to see what happens in the forward flank. Terrible position. Okay? Now, if the storm is moving this way, being a right mover, maybe you're fine. But if you're right there and the storm is moving that direction, guess what? You may get the rain, you may get the hail, you may get the calm, that little area right there, and then you'll get the tornado. That always was kind of the wives' tale. There's a calm before the tornado. It depends on where you are in relation to the storm. If that person is down here and the storm is moving that direction, you may not get a drop of rain, but your house is destroyed from the tornado. So it all depends on the movement of the storm and where you are in relation. Okay? The low-level features, though, you can't see anything. I mean, that's what you're going to see. The huge shelf cloud, all that ugliness, that's coming right for you. You better be hightailing it out of there or going indoors or something because you're about to get hit. Okay? That's all the ragged clouds along the forward flank downdraft that's about to get you. So dark horizon means obviously a lot of rain. It's directly headed towards you. Not good. That's not good. There's all that greenish sky, bluish green, right? What did we say that was? Hail, right? Right? So yeah. So once again, ragged appearance. So again, you're about to get hit by the outflow with a thunderstorm. Again, then you start getting the hail. I'm amazed to see how many chasing videos there are that I guess I don't know if they're wanting to be in that, but you know, they'll always get pummeled. I don't know what their insurance companies are saying. I mean, after about the third or fourth hail event, you would think they'd say, "What are you guys doing out there in the middle of Kansas?" It seems like you're always you're not at the house, and you're always in a weird position. I actually know a lot of people that actually go and they'll rent rental cars. They get the insurance, and it's like, hey, if it gets hailed on, it's not your own car, and they'll rent it for a day and then do that. But maybe that's why our rental rates are going up, because we're paying right for all these storm chasers insurance issues. Yeah. So again, can you see the action area? The answer is mainly no. This is the forward flank. Okay, that's what you get in that area. So not good. So please avoid it. Okay, the right flank right here. Okay, nearly always the best position if this storm is moving in that direction. Again, not a great place if it's moving that way. Okay, but you will be able to have the best spotting like this. Okay, storm is going to be moving in that direction. You have a beautiful view of the rain-free base and everything else. Cauliflower tower getting tilted. Okay. Remember, the heavy precipitation is often to the right. If it's moving that direction, that's where the heavy precipitation is, and that's where the rain-free base is going to be. Good picture there. Yes?
Is the storm always in that shape, even if it is moving east or south?
A lot of times, it will actually keep its shape like that. If it's a well-balanced thunderstorm, where the exhaust and the fuel... Yes. Yes, very often it will stay it'll stay that shape for quite a while, especially if it's...
Even during Gerald, it was
It was a little bit messier. This is a classic textbook where you get a lot in Kansas, Oklahoma. I will say everything's a little bit messier looking when you go south of that area, especially here. We could have this. Ours will look a little bit not as good. Might be able to make out the kind. Oh yeah, I kind of see the hook in there, but it's.
The general idea of that is always.
That's where the rotation is, right there. That's why it's hooking around. Yeah. Correct. Right. Gerald was not opposite where the hook was up here and it didn't. But it just moved down. Yes. Yeah. It actually moved along a boundary. Yes, sir.
Where do you see or tend to see the round soft under clouds?
Oh, the mammatus clouds. Yeah, a lot of times those are actually underneath the main cirrus shield. So you'd see it sometimes on the backside here, kind of like this. If you were looking at the thunderstorm, sometimes you'd see the mammatus clouds all around the edges like that. Those are just severe turbulence clouds, is what they actually are.
So when you talk about the column up there getting lifted up, and you have one moved off to the right, and it's moving
Yes.
clockwise, the left one being clockwise, could that potentially form a clockwise tornado?
Correct, yes. And the few instances that we actually have of clockwise rotating tornadoes very often are with that left mover supercell that tends to die out. Most tornadoes, most documented tornadoes have all been counterclockwise rotations, but there are a handful of clockwise rotation. Yes, in this hemisphere. Even in the southern hemisphere, the tornadoes still rotate counterclockwise. That rotation is small enough that the Earth's rotation doesn't affect it. Big rotations like hurricanes and typhoons affect it, and that's why those rotations are different. But for small rotations, like on the scale of 1 mile or a half a mile in rotation, the Earth's rotation, the Coriolis effect, isn't affecting that rotation. It's actually how the storm is forming is creating the counterclockwise rotation on that. Look at the dusty inflow coming into that thunderstorm there. There's a tail cloud. Again, precipitation movement is tended to be away from you at this point. And that one's a little bit dark, can't really see it much. Oh, that's a half-mile wide tornado, that's why. I thought it was just rain. Oh no. Right? So let's see what we've learned. We're going to take a short quiz here. We're going to decide here's our spotter, and we're going to put you on this supercell. So like this is not you can kind of see this is a supercell. This is producing a good tornado, but this is not classic looking where you have this hook. But if you kind of use your imagination here, there is a hook here. It's just not as classic as what we've kind of seen before. Okay, so where are we going to be? In this case right here, we're viewing it from where this guy is right there. So we're looking on this back flank, which is actually a pretty safe area, especially if the storm is actually moving that general direction. So is he safe? Yeah, the storm has already pretty much passed. He's on the south flank of it like that. Okay, where do you think this guy is watching? Here's some blue sky. Here's this area here. Here's all the downdraft. You take a guess as to maybe where he is positioned in this case. He's actually where he's supposed to be, to where you actually have perfect viewing of this. And so again, as long as the storm is moving in that direction, you're going to be safe in this spot. What about this one? Here's the shelf cloud. We kind of had a picture like this before, and that was kind of a bad spot, right? Because this guy's like, it's about to hit you. So not good there. Okay. Ooh, what about this one here? Yeah, where is this guy? Yeah, you're right smack dab. If you're probably looking up, you're probably actually seeing the spinning clouds right above your head. So safe? No. Yeah, I guess I need to replace that with a bad emoticon, right? With the tears or the frustration or something. I don't know. Right. Yeah. So wrapping up, let's kind of talk about our radar real quick. Operates 24 hours a day. It's always spinning out there, and of course, this is one of the main tools. We upgraded it back a couple years ago, not this whole thing, but the inner workings of the actual radar itself, and I'll explain that. Radar, radio detection, and ranging, okay? So it's sending out a pulse of energy, and then it's listening. It does the majority of listening. Like 90% of the time, it's listening. It's the receiver and not the transmitter. It's doing both at the same time. 2,000 pulses a second. It is sending out energy, listening for a reflection. Okay? Raindrops, hailstones, bats. Small objects in the atmosphere will reflect back to us, okay? And so that's what we're actually measuring. Now, the new upgrade sends out not only a pulse on the horizontal plane, but then the next pulse is one on the vertical plane. What that does, that is creating now a three-dimensional picture of the object that is falling from the sky. Raindrops fall as a hamburger bun. They are squatty. It's not like the cartoon, which shows this raindrop, this teardrop that's falling. When the bigger the drop, the flatter it actually gets because of the drag that goes around it. So it creates more of a hamburger bun shape. That shape has more of a horizontal as opposed to a vertical cross-section. And the radar can pick that up. So it can now discern what are spherical hailstones, which are mainly round, or at least tumble in a round shape, as opposed to squatty things like raindrops. We have a much better estimate of rainfall now with our upgrade as opposed to what we did maybe even 5 years ago. So it's able to take out the hail when it's computing how much rain fell on the ground, which is kind of pretty handy. It can now, because again, snow has a simple shape, or a much different shape. It can usually discern then between sleet stones, which are round and spherical, as opposed to a snowflake, which may have a very long horizontal like that. So it's doing pretty good. We don't have a lot of different chances to view snow here, so obviously, right? Distance is an issue with radar to where I don't show the Earth curving. The radar beam is actually going straight and the Earth curves, which means that the further the storm is away, we cannot see the lowest levels of the thunderstorm actually. So the closer the storm is to the radar, the better. We also have a cone of silence, meaning that we cannot tilt the radar directly above to actually see the thunderstorm over our own office. We have to use a surrounding radar to actually see that. We have a new thing called sails, which in fact, remember I talked about we get a radar picture every 5 minutes? Well, in fact, what happens is that now we've changed the computer programming of this to where now it starts its main tilt, does several tilts, and then it quickly goes back down to the ground and gets another tilt, and then continues back up. So we're actually able now to get a picture about every 2 or 3 minutes, as opposed to waiting to 5 minutes. So that's helped us out. We can actually see some of these smaller tornadoes quicker now because we are actually getting a quicker picture. One product that you'll see is base reflectivity on your apps. That's what you typically see on TV. It's called base reflectivity. That's just the lowest scan, what kind of reflectors we have. Now notice in a thunderstorm though, we have an area like in this middle part of the cloud that has even bigger pieces of things. And those are a higher reflectivity called 60 dBz. That may be hail. Well, you won't see that on the lowest scan of base reflectivity, but on composite reflectivity product, it takes all the different levels and it shows you what the biggest one was. So the composite reflectivity product will always look worse. And we actually use that to kind of see some of that hail in the middle parts of the thunderstorm first. This is what base reflectivity looks like. Composite now has this white. So it's actually seeing that middle hail and it's actually bringing it all the way down to the ground so we can see it. So it's a way of looking at the 3 dimensions of the storm in kind of 1 dimension. So that's the difference between base reflectivity and composite reflectivity. We can also get echo heights, or the tops of the thunderstorms, estimates. In this case, 62,000 foot tall thunderstorm. Okay? So we can get estimates of that. We can get estimates of the amount of water in the actual thunderstorm. We can use this as a hail indicator. It's called VIL, vertically integrated liquid. And so high levels of VIL will typically correlate to hail chances and the high hail. This is a picture of our rainfall estimate that we had back in the October flood of 2013. Did a very good job, doing very good with 1 hour storm totals. And so again, once we went to dual pole, we saw a really big increase in the amount of really good rainfall data from our radar. Still need the COCORAs though. We still need actual rainfall totals because there are days where the atmosphere will give us very poor estimates. Okay, the radar isn't perfect. It's good, but it's not perfect. And so we still need that ground truth data. And then here's a picture of some dual pole products that we could get, which actually, that's actually a hail spike, which is fairly interesting. That's actually giving us a clue that that right there is hail. It's called a hail spike. These are just some of the other products we'll get on this new dual polarization. Here's a 3-body scatter spike. This is hail. And literally what's happening, the energy is going, hitting the hail, and it's taking longer for it to come back to the radar because there's so much reflection because of the hailstones. It's fooling the radar, thinking that that stuff is further away. And that's why it's coming up and it's creating this dummy sort of reflectivity there. So when we see these spikes like that, we know that it's probably hail that's actually falling. And those are some images too of that. So. Well, it depends on the radar. In these cases here, like in this case here, the radar that's shining is over here, shining this direction, like that. If we were using an image of the San Angelo radar, which is up here, that spike would probably be down here, like that. So it's, yeah, it's on the back side of what it's seeing, and it's all from the reflection. Yes? Yes? Most likely, they're taking it from the lowest level of the radar. If they're showing velocities on like the Weather Underground app or whatever like that, most everything that you find on the internet is always the lowest scan. It's not until you get into some of the other apps that have the different tilts of the radar that you can actually do some investigation like that. That can go. So let's get the sheets. Do you have all the sheets? Let's pick a winner for the, can you get the rain gauge on the, oh, yes, 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 thank you. We need some help, believe it or not, besides just being a spotter. We have other volunteers in the Weather Service. They call them cooperative observers. You shuffle them real good. And these cooperative observers have a much larger rain gauge than this, believe it or not. It's a metal rain gauge. They also have a temperature gauge at their house. And part of the climate data of the United States is that they will actually give us daily weather information, the high and low temperature of the day and rainfall. We had a volunteer near Cedar Creek for years. They're no longer able to do that. And so if you live near Cedar Creek and you are willing to be a volunteer for the Weather Service in getting us to put equipment on your property and do a daily report for us, it takes a few minutes in the morning, get the high and low temperature. It's all computerized equipment. We maintain the equipment. We'll give you everything that you need to do it. But we need a volunteer to do that, because what we don't want to do is have us not have any climate information from the Cedar Creek anymore. We like to keep it fairly steady. Yes, sir? Oh, very good. Would you maybe be willing to talk to somebody about that? Thank you so much. Go ahead and let's give him the sheet. And if you, can you stay like 1 extra minute or so afterward that we can talk to you about it a little bit? Okay, thanks. Go ahead and give him that sheet like that. Okay, let's give away the rain gauge. We have shuffled the papers, correct? They are, the Office of Emergency Management says they're shuffled. Okay, we have a lot of people here, so I want someone to shout out a number between 1 and 20. What did you say? 13. Lucky 13. I was born on the 13th, so it is very lucky. I was born on Friday the 13th. I know. That's either good or bad. I don't know which one that is. Okay, so I'm going to pick the 13th sheet, and that will be the winner. Of course, if you win this rain gauge, you have no excuse to not join Kokoraz. We'll be watching. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Lucky 13. Deborah Talley. All the way in the back. Congratulations, ma'am. For those of you that did not win the rain gauge, I apologize. Now, there are a couple of other trainings we're doing the rest of the year. If you would like to show up just to try to win a rain gauge, you can do that. I'm not going to stop you, but you have to stay for the entire training again. Okay? And if you do not win one, obviously, and you want to buy one, on the Kokoraz website is a store where you can actually buy the rain gauge. It's about $30, like that. So I encourage you to do that. So I thank you guys for coming. Thank you so much for being trained weather spotters. I will say that if we ever do call you, it'll come across your caller ID as U.S. government. Don't freak out. Okay? Very often we will have to start leaving a message before someone is brave enough to pick up the phone where it says U.S. government. Yes. Yes.
All the other training you have are about the same, or they can be longer or shorter. Do you change anything?
We typically change it around a little bit each year. We try to add new videos. But no, if you go to one of the other ones for the remainder of the year, you're going to get the exact same thing. Yeah.
And also, do you need any volunteer in Lee County?
In Lee County?
Yeah.
I don't know. At this moment, I don't think so. I don't think so, like that. So anyway, oh, yes, sir.
I have a quick question. Is there ever a snow wrap tornado? Is that a possibility?
A snow-wrapped tornado? The answer is typically not. You can get thunder snow. It's sometimes somewhat common that if you are unstable enough, even though it's cold enough to snow, you still actually have a thunderstorm. But I mean, in a thunderstorm, there's a lot of snow. Now it just all melts to rain by the time it comes down to the ground. But there's typically not the dynamics needed to get there to get a tornado and snow at the same time. I don't want to be on there. I don't want to be that day. Yes, ma'am.
How much impact does the mid-oceanic elevator have?
The mid-oceanic elevator. We'll ask the newest meteorology student. What are you referring to when you say the mid-Atlantic Ocean elevator?
It's the current in the ocean.
Oh, okay, the ocean currents.
Yeah.
Yes, yes. Well, because the Earth is covered by 70% water, obviously the ocean, there's this battle in meteorology, like what comes first? Does the ocean affect the weather, or does the weather affect the ocean?
Yeah.
Depends on if you talk to the oceanographer or the meteorologist. We think we're we're causing the ocean, no, we're causing the weather, kind of a thing. So just like we're seeing with El Nino and La Nina, when you change ocean temperatures, which comes to the currents and everything, yes, you can change global weather. So I can't tell you how much it causes the weather right here, but I know it is an interaction.
It turns over south of the
Yes.
British Islands.
Exactly. So whenever you start changing water temperatures, you can change the weather. So it can definitely affect it. So we're going to be here afterward for several minutes. So if you have other questions, please come and ask. But if not, thank you guys so much. Enjoy the rest of your day. Enjoy the beautiful winter weather, which is, that's why we live in Texas, right? That's why we live here. So thank you guys very much. Appreciate it.